So, as a reminder, what have we learned so far? First, decentralized digital money requires a system where the majority votes on the same history of transactions. And second, voting power must not be determined by the amount of computers one has in the network. So, how does Bitcoin solve this? The clever solution from Bitcoin is mining. Not the typical kind of mining, but a digital one. Lots of computers will compete in a race for a cryptographic puzzle, and whoever solves it first receives a reward in the form of new bitcoins. This reward is the way that all bitcoins are actually created. It started as 50 bitcoins in 2009 as reward and is halved every 4 years until the reward is eventually zero in the year 2140. And all 21 million bitcoins will have been mined. This cryptographic puzzle is something that can only be solved by brute force calculations, meaning a computer just has to try again and again as if it was trying to guess a password. So a majority in a Bitcoin network actually refers to the computing power for the cryptographic puzzle. And now you cannot just have multiple computers for more voting power. You need more computing power. That might sound quite similar at first, but actually it solves our problem, because getting more computing power now actually comes at a significant cost, especially the more and more the network's total computing power grows. Yeah, you can of course still have Shirleys in the Bitcoin network, but to have Shirleys, or Sybils, it's not as easy as it was before, because before you were just needing to have multiple computers with multiple IP addresses. And those, if you remember, are extremely cheap to get. You can get thousands of instances with just a few dollars. But now, to get more voting power, you need more computing power. And it's a very specific kind of computing power. Especially given how large the Bitcoin network is already at the moment, it would cost millions, if not billions of dollars to get a significant amount of the total computing power. And because we are having a vote from the majority, you would actually need to get 51% of the total computing power to attack the system, which would cost you billions these days. And you would have to spend it all on these specialized machines, which are not good for anything else in the real world. The calculations have no further meaning, but that's an intentional security feature. If you're going to attack the system, you need to invest so much money into machines that are only useful for the system that you are attacking. So we're making it really expensive to attack Bitcoin. The puzzle is based on a cryptographic hash function. In Bitcoin, it's SHA-256. In Ethereum, it's Keccak-256. But they are both very similar. Those are just different versions of a hash function achieving the same thing. So what is a cryptographic hash function? It's a function that is irreversible and unpredictable, and it produces a digital fingerprint. Take this, for example. Here you can see a live calculation of the SHA-256 function. Basically, any data you put into that function will produce a so-called hash as a result. The hash uniquely identifies the original data. So here, only ABAA will create exactly this output here. The hash itself is just a random string of data. But because the hash function is irreversible, you couldn't just look at the hash here and determine it was ABAA as input. But when you know the input was ABAA, it's very easy to confirm that this hash here is indeed coming from that input here. So take this hash here. Now, how would you know its input? As you can see, the function here doesn't work the other way around. So your only option would be to try every possible input at hand. For example, you might try numbers first and count up. So you do 1, no. 2, no. 3, still not. And so on. Eventually you come to 88484. And yes, this was our original hash function. Now, the puzzle in Bitcoin goes like this. Given some data, for example, hello world exclamation mark, find a number to append to the data so that the SHA-256 hash of it starts with at least a certain amount of zeros. So, for example, here we can easily calculate from hello world 0 to the 1312 hash. But again, if you only have the 1312 hash, you cannot calculate what the original input was. So now all we can do is just calculate as many hashes from different inputs. Eventually, we will find 4250, where the hash has 4 zeros in the beginning. 4250 will be the solution for the puzzle, and it's also called a nonce. And of course, the more zeros you require in the beginning, the higher the difficulty to find the correct solution. And it's pretty obvious why, right? Because the hash is just a random string. Just probabilistically, you need to calculate more hashes until you get one with more zeros in the start. And this difficulty of the puzzle is changing the stronger the network's computing power becomes. So in the next chapter, we can look at how this mining relates to voting on the same history of transactions.